So, good morning. So today I'm going to talk about examining conditional language model. So the reason the slides are on my website is I've given the talk before, so I could rehearse a little bit. So this is mainly the work of Juliette Fay, who is one of my PhD students, and she's funded by an EU project, which is an ITN, an innovative training network. So it's a network of PhD students for the consortium of European universities. So the ITN is called NL4XAI. And because of that, she has a co-supervisor, Albert Gatt, who is at the University of Utrecht. And she also had to do a secondment at Orange in Lannion. And so, she also works with those people here, Quentin Brabant, Lina Rojas Barahona, and Gwenole Le Corvée. Okay, so language, sorry, and I wanted to say something else. Sorry. Yeah, so the talk is about examining conditional language models, and it's about methods that can be used to identify what kind of errors these language models are doing, understanding why they are doing it, assessing how much impact it has on the performance of the model, and trying to understand where the error in the model the error comes from. So language models map an input to an output using a lot of neurons, and because we don't know how these neurons work together to arrive at the final output, we can say so these language models are said to be uninterpretable. They are not directly understandable by human beings. So they are not interpretable, but we can try to make them explainable, and that's basically what I'll be talking about here. And we can develop methods which can help explain to a human being how the model behaves. Why it makes some errors, how much errors it makes. And today I will discuss three different methods, three different ways in which you can improve the explainability of those models. The first thing is to have fine-grained evaluation metrics. So instead of having, like we often do in generation, instead of having metrics that are global metrics that will give a global score to the text generated by the model, you can develop fine-grained metrics which are specific to a certain type of error. So they allows us to quantify, to detect a specific type of errors, and to have an idea of what kind of the errors the model is doing. A second way is to use probing methods to understand where a certain type of error comes from. What kind of the model architecture is most likely to induce that type of error. So it's called probing, and I will present some probing methods we developed to detect, to understand where omissions come from in conditional generation. And the other way you can improve the explainability of the model is by having sort of architecture that are explainable by design. And here the idea is to have the model provide intermediate, non-latent results that allows us to have a better understanding of why the model, of what impacts basically the performance of the model. And I will look at two types of conditional generation tasks. The first one is knowledge graph to text generation. So where the task is you have as input, you have a knowledge graph, and as output, you want the model to generate a text that verbalizes the content of that graph. And here I will focus on semantic adequacy because the task is really you want the output text to match the content of the input. So there should be, there should be a sort of semantic equivalence between the two. And so I will be focusing on semantic adequacy and developing method to better explain, how does the model behave in terms of semantic adequacy? So which type of errors it makes, where the errors come from, and where the errors come from. The other type of conditional generation task I will be looking at is knowledge-based dialogues. So the idea is to generate a response given a dialogue context that includes both a dialogue, the preceding dialogue, and a knowledge graph. And here I will focus on the impact of errors on coherence, on the coherence and cohesion of the dialogue. And here I will more focus on discussing how a specific model architecture helps us to better understand what impacts these two factors, these two dimensions. Okay, so the first task is knowledge graph to text generation. So as I said, the task is to convert a graph, a knowledge graph, into a text that verbalizes the content of that graph. And here you have an example. So typically we are looking at knowledge RDF graphs, where it's basically a graph is a set of RDF triples or binary relation between entities. So the nodes in the graph are the entities, and the edges in the graph are the relation between the entities. So you have this input graph, and then you want to generate a text, such as the one showed at the bottom of the slide. And an important thing to note here is that so a knowledge graph is a set of binary relations between entities. So basically 2/3 of the input are entities, and so in the text you should find those entities too. So a large proportion of the output text basically describe entities, and that's what I'll be focusing on here. So I will be talking about, I said, semantic adequacy, so how much the generated text match the input graph. And we know that language models in general have a tendency to hallucinate, so they often generate information that is text, or generate information that is either not factually correct, but also if you are doing conditional generation, so where the output is conditioned on the input, and so it should in some sense match the input, it can also hallucinate in the sense that it will produce a text that is inconsistent with the input. So this is hallucination. I will not talk, so there's a lot of work on hallucination. It's a well-known fact about language models. They often hallucinate. And here I will not talk about hallucination, but about omission, which is, if you like, the inverse case of hallucination. So the case where the generated text failed to omit some information that should actually be present because it's present in the input. So here is an example of omission. So here you have a linearized graph, right? So it's a set of triples, as I said. And all the entities, so the entities in red are the entities that are not mentioned in the generated text. So you have in the input you have 6 different entities, but in the output, in the generated text, you only have three of these entities are actually mentioned. In the rest of the talk, omissions are basically entities in the input graphs that are not mentioned in the generated text. So one first thing we do to have a better explanation of how well does the model generate text that match the input, so how good is the semantic adequacy of the model in terms of omission. One thing we can do is to have a fine-grained metric. So in conditional generation, we mostly use global metrics, which basically give us score the quality of the generated text. So it's a global metric in the sense it doesn't give any detail, it just says this text has that score. So instead here what we do is we have this fine-grained metrics that tells us how much omission the model is actually producing. And we'll talk about 2 different metrics we introduced, so entity-based semantic adequacy and entity-based semantic inadequacy. So the first thing we do is we have an algorithm for detecting omissions. So the idea is you have given a graph and a text. The graph contains a set of entities, and the algorithm should should find out how many of these entities are actually mentioned in the generated text. So to do this, we have the set of entities we are looking for, and we have a text. And we basically combine different existing methods to find out whether an input entity has a corresponding mention in the generated text. So we use an entity linker. An entity linker, basically, given a text, will find in that text the text spans that denote a knowledge base entity. And in our case, the knowledge base is DBpedia. So we can use an entity linker, apply it to the text. It will tell us from that text which are the knowledge base entities that are mentioned in that text. We use approximate string matching, so where we compare n-grams in the text with the entity names in the input graph. We use pronoun resolution to resolve pronouns. In the text, they are pronouns, but of course, they're not entities. So we first resolve them, and then we do approximate string matching on the antecedent and the graph entities. And we use a date parser to normalize dates both in the input and in the input graph and the output text. So combining these different methods, we get a list of entity mentioned pairs, and then using that, we can detect, what are the entities that have no corresponding mention. So we evaluate this algorithm on a benchmark, an existing benchmark that is manually annotated. So we have, for each graph text pairs, we know which entities have been mentioned. And we got a precision of 83 and a recall of 82. So most of the omissions that are detected are correct, and many of the existing omissions are found. We also have a qualitative analysis where we compare texts for which we actually detect omission, but which have high human semantic scores. So I'll get back to this later, but there is a human evaluation of the generated text. So you can look at those cases, and in those cases, we found that, in fact, the algorithm was correct in the sense there were indeed missing mentions, and in 10 cases we had missing mentions where even for the human score was actually high. And in the other case, it was degenerate text. Okay, so once we have this algorithm, we can compute what we call entity-based semantic adequacy, which is simply the proportion of entities in the graph which have no mention in the output text. So in the example we had before, we had 6 entities in the graph. 3 of them were mentioned in the generated text. So we have an entity-based semantic adequacy of 50%. And then, so that's at the instance level, so you can do this on the graph text pair, but then when you want to compare and evaluate models, you want to do this on a more general level, so basically based on a larger data set. So you can do this we do this in 2 ways. We use the average entity-based semantic adequacy, so the entity-based semantic adequacy average over the whole corpus. And the other thing we compute is the proportion of texts which have at least one undetected entity, so at least one omission. And so we apply this metrics to the output of the participant of the WebNFJ shared task. So this shared task is about about generating text from graphs. And so we had two sessions of this shared task, one in 2017, one in 2020. And in total, we had 25 models participating. So we can look at the output and find out, how much the text generated by these 25 models omits some of the graph entities. So in 2017, it was the first edition of the task. The language models were not as good as they are today. There were also some, in the participants, there were still some statistical models or some rule-based models. But so in this first edition, we find that 10 to 70% of the generated text have at least one omissions. And for 6 out of the 9 models, you have 40% of the generated text which have at least one omission. So in this first version, omissions were very, very frequent. So in 2020, the models were much better. The task was known. So the histogram, so the x-axis is a proportion of text with at least one omission, and the y is the number of models that have this proportion. So you see that we have, in 2020, you have 5 models that have the top 5 model, for the top 5 models, the generated text omit at least one entity 5% of the time, so it's much better, but it's still there. And then the remaining 11 models omit at least one entity 10% of the time or more, so it goes from 10 to 50% of the time for the worst model. So as I said, normally we use in generation, we often use this very global matrix that gives us a score for the model. So it tells us, for example, the blue score of the model is a certain level. And a high blue usually means that, the high blue means that the model generates texts that are close to the goal text. Right? So it's basically comparing what the model generates with the expected text. So what we wanted to see is, in terms of omission, how well does blue capture the fact that the model does or does not omit some input information. So in the figure here that you can see, probably the top part is basically, so we rank here the models by blue score and by AZ score, so entity-based semantic inadequacy. So the top part of the model, of the picture, give you all the models that have the highest rank in terms of blue. And the right part of the picture gives you the model that are highest rank in terms of entity-based semantic inadequacy. And so what you see is that, in fact, there's only, of the 8 models that have highest blue rank, only 3 have high AZ rank. So that means even though they have a high blue score, they still omit, only 3 of these 5 models have a reasonable level of omission. The other 5 have an AZ score that range between 10 and 20%. So on average, they fail to mention at least one of the input entity 10 to 22% of the time. Right? So the message here is simply that blue does not tell you how much the model is omitting. You can have a high blue score and still omit quite a few entities. So still generate incomplete text. So more generally, we compute correlation with both with human, of semantic adequacy, of this entity-based semantic adequacy, both with human judgments and with the other existing metrics that I use in generation. And what we find is, the thing we were mostly interested in is how well does it correlate with human judgment of semantic adequacy. So there is a human evaluation of the model output where we basically ask human beings, human annotators, to compare the text that is generated with the input graph and carefully check, is all the information that is in the graph also in the text, and vice versa, is the information in the text actually present in the graph. So do the two actually match? So we have these human scores for semantic adequacy, and ideally we would like our metric to actually correlate with human judgment of semantic adequacy. So we found that, and we do this on the human evaluation of 17 and 20, we get slightly different results because the protocols were also different, the data is also different. Basically, we found that there's a sort of moderate to strong correlation with human judgment of semantic adequacy. And the correlation with global automatic matrix, again, vary from one year to another. But again, you see that the correlation with blue is actually not so high. And so to conclude this part, you can use a similar idea to detect hallucination. So here, using only the entity linker. So remember, the entity linker basically goes through the text and can find mention, entity mention in the text. So it processes the text and it tells us what are the knowledge-based entities that are mentioned in the text. So if you compare the entities that are found by the entity linker with the entities that are in the graph, and you find some of them are not in the graph, then you can say they are hallucination. So what you see here, the first column tells us what the automatic detection does. Then we have this manual evaluation. We only did this on 144 random text. But we so manually checked what the entity linker was telling us in terms of hallucination, and you see it has reasonable quality. So most of the automatically detected hallucination actually are hallucination. And here you see again, so these are the top part of the picture are the 2020 models, so the better models, and the bottom part, the 2017. But you see that there's still, even in 2020, so Orange was using T5 or BART, one of the, at the time, recent models, and it still has a lot of hallucination there. Okay, so then we looked at what kind of text contains these omissions or have these omissions. And we found basically there's three main types of cases. One of them is when the text that is generated is short with respect to the input, so it's basically not verbalizing the whole input. Right? So here you see there's two entities missing, the text is very short, it just does not account for the whole graph. The other case is hallucination, where here, so you have this relation of birthplace between Lady Munson and Darlington, but in the text it's not at all. I mean, you have completely different entities. So you can see this as an hallucination in the sense that it generates entities that have nothing to do with the input. And but here it's also substituting for the entities that should have been there. So it creates an omission. It creates both an hallucination and an omission. And the other case, which is not so frequent anymore, but used to be in 2017, is that when you have text that is word salad, basically. Okay, so we found that there are omissions. Is there a clock somewhere? Yeah, 24, okay. We found there is omissions, so, and then the next thing we did is, could we find out where these omissions come from in the model? So to do in conditional generation, mostly we use what's called the encoder-decoder models, where you first encode, so you have two networks. The first network is the encoder, which is going to create a representation of the input. So in our case, the graph is the input, and it's mapped to a vector of real numbers. So you first create the representation of the input using the encoder, and then you decode from that representation to generate the output text. And so our hypothesis was that these omissions, they were mainly that the encoder was mainly responsible or play a big part in omission. Our hypothesis was that the embeddings of graphs that contain omissions, so the embedding of the entities that are omitted had a weak signal. And so we wanted to test this hypothesis by probing the encoder. So we use two methods for probing the encoder. The first one is a parametric, standard parametric classifying probe, and the other one is a non-parametric method, which is based on the similarity of the graph encodings. So how do we do this? Well, the first thing we do is we generate. So we want to test, does the embedding of an omitted entity differ from the embedding of a non-omitted entity for a given model, for a given generation model. So the first thing is we take a generation model, we use it to generate text from graphs. So we create this big data set of graph text pairs. Then we annotate the generated text for omission. So we go through the data and we use either the automatic detection or manual annotation to annotate the graph text pair for omissions in the text. And finally, we can use this annotated data to train and test the probe. So the probe will tell us, can we distinguish those entities that are omitted just by, from those that are mentioned just by looking at the embedding of the input graphs. Okay, so which generation? We looked at two generation models, T5 and BART, so they are both pre-trained encoder-decoder models. We take those pre-trained models, we fine-tune them on the WebNLG dataset, on the training data, so about 47,000 graph text pairs. Yeah, the graphs are from DBpedia and the texts are crowdsourced. Right? So we train the model on this, so then we have a model that can generate a text given a graph from DBpedia. Then we apply it to a large set of input graphs, which we take from Kelm. So we take the graphs from web energy, but also the text, the graphs from Kelm. So Kelm is a data set created so it's actually from Wikidata in this case. So it's basically subgraphs of Wikidata that have been extracted, which vary which contain from 1 to 6 triples, so similar to web energy graph size. And so we use this other data set to have more variety in terms of entities and properties. Okay, so we create this large set of graph, and then we apply our generation model to this graph to generate the text using our model. And at the end, so we permute the input to have more output, and we filter the repeated output. So in the end, we end up with about 71,000 graph text pairs, where the texts are generated from these two models. And now we want to see how many, where are the omissions in the generated text. We want to label them, so we can actually train and test the probes. So as I said, we can use either the automatic detection that I presented before to annotate each text for omission. So it's not perfect, but at least it's fast. So we can do this on all text. And we also have a manual annotation to see how much the results differ depending on whether you do this imperfect automatic annotation or manual annotation. So we had three students annotating the data, and we have this kind of agreement between the annotators. And we do this for 13,000 texts. And then when we do this manual annotation, we observe that there are things that are not quite omission, which we call distortion. I will give some example afterwards. So it's a case where you don't really have the correct mention for an input entity, but it looks very much like it's very close to it, right? So I'll give some examples. It's basically spelling mistakes or dates that are almost correct, things like that. And so they are incorrect. It's still not semantically adequate, but it's also very different from omission, where an entity is not mentioned at all. Okay, so we label our data, our text with information about whether or not they contain omission and distortion when we have the manual annotation. And then we are going to use this data to train and test our probes. So here is the example of distortion, right? So you have the RDF entities on the left, and the mention is on the right, and you see it's not correct, but it's very similar. So for these, the manual annotation would say it's not an omission, it's a distortion. Okay, so the first one, so as I said, we have two probes. The first one is parameter-free, so it's not a sort of classifier, it's not something you train. It's just basically comparing. So the idea, remember, the idea was that the omitted entity, our hypothesis, has a weak signal. So our idea was, well, if you take a graph and you replace, so this is the thing at the top, the graph with an omission and a mention, and you replace the omitted entity with a known symbol, then the difference, the difference between this graph where the initial graph and the graph where you substituted the omitted entity is small, and it's in particular smaller than the difference between the initial graph, and the graph when you replace a mention, because a mention would have a richer signal, so it would be more specific in a way. The embedding would be more specific for mentions than for an omission. So this was our idea. So we said we're going to compare the similarity between a graph where you've replaced an omission and the similarity between the initial graph and the graph where you substituted a mention. And our idea was that, again, the difference, the similarity should be higher for the graph where you substituted the omission than for the mention. So this is what we do. We just average. So there are multiple mentions in a graph. So we compute the similarity between the graph and each of the so the average similarity between the graph and the graph where you've removed a mention, and use the same thing for the omission. And then you compute. What we do is we compute the ratio of graph such that the similarity between the graph and the graph where you've removed the omission is greater than the similarity between the graph and the graph where you replaced a mention. And here are the results. So we have different data sets, so in domain and out of domain. So O is for omission and D is for distortion. And the top part of the figure is for the manual annotation, and the bottom part is for the automatic annotation. And basically what you see is that for omission, so if you look at the all column, that in 68% of the cases, it is true that the similarity, so our hypothesis is true that the similarity between the graph and the graph where you substituted an omission is greater than the similarity between the graph and the graph where you substituted a mention. And then we do this also for both omission and distortion. And you see omission and distortion have a different behavior. So the distortion are not so easy to spot, which is what we expect because they have a name, something that is very similar to the entity. And the other interesting thing is that so when you are out of domain, where you are on entities that have not been seen at training time, or rarely been seen at training time, again the difference is not so big. Which again, which we hypothesis is again because since the entities have not been seen, they also have weak signal a bit like omitted entities. Okay, so that was the first probe, and then the other probe is a more standard probe where you train a classifier whose aim it is to predict, given a graph and an entity, whether that entity is going to be omitted or not. Which we train on the data I just mentioned, so the annotated data I just mentioned. So here we experimented with different classifiers, but the best one was a two-layer, multi-layer perceptron. And it's trained, you give it the encoding of the graph, the encoding of the entity, the label, so is the entity omitted or not, and then so the label is 1 if the entity is not omitted and 0 otherwise, and you train this classifier. So you can see this kind of classifier as a sort of modeling the sort of quote entanglement relation between a graph representation and an entity. It will be 1 if the graph contains the entity, or and 0 otherwise. And again, so you see that so the classifier for omission has almost 70% accuracy, or and you see again there is a distinction between omission and distortion, which in this case goes the other way as before. Right. So in the previous case, the distortion were harder to distinguish the similarity between the graph, the original graph, and the graph containing the distortion was closer to the similarity of the graph and the graph where you've removed a mention than the same comparison for omission. But here for the classifier, we don't have this, so we have that somehow the distortion are easier to spot. Okay, so then you need to. So we wanted to compare this classifier with different alternatives. So an obvious alternative is, as an upper bound, is to say we're going to look at a classifier that tries to determine whether an entity is present or not in the graph. So not whether it's going to be omitted, but whether it's present in the graph. And then you see it's the classifier is actually quite good at this. It's got 97% F1. And so again, you see that it's detecting an omission is possible, but it's not as easy, of course, as detecting a missing entity. So, sorry. Which way is it? It's going the wrong way. 51, 50. How do you go back?
I think you can always hit the keyboard.
Yeah, no, it's okay, I think 47, 46. Okay. Okay, yeah. So another control task is you want to check whether the probe is actually evaluating the embeddings or whether it's memorizing the data. And one way to do this is you can randomize a label and see what happens. And then you see that, and then you compute what's called selectivity. So it's a drop of performance between the probe trained on the real data and the probe trained on the randomized data. And you see the probe trained on the randomized data is really, really bad. So definitely the classifier is learning to distinguish the graphs that contains omission from those that don't. We also looked at hard examples, so cases where the same entity, depending on which graph, depending on the graph it occurs in, the same entity is sometimes omitted, sometimes distorted, and sometimes mentioned. So the idea was to check, can you predict whether an entity is mentioned simply from the entity itself? And in fact, we see that we can't, in the sense that these entities here, they are, so M and O means the same entity is both mentioned and omitted, depending on the graph it occurs in. And again, we can distinguish whether it's a mention or an omission, so we can predict whether it's an omission, 80% of the cases, and this is true for all of the combinations. And then, so this first experiment was done on BART, and we did a similar experiment on T5 to see whether it was a specificity of BART or whether it was generally true that you can detect from the encoding of the graphs whether an entity is going to be mentioned or not. And so we do the same experiment on T5, but we only did the automatic annotation, and the results are stronger in this case than in the previous case. So you have the non-parametric probe, the NPP is non-parametric probe, and the PP is parametric probe, and you see the scores are higher than before. Okay, so in summary, even though people talk a lot about hallucination in conditional text generation, particularly in that case where the text really has to match, the output text really has to match the input, we find that the generated text is often incomplete, so inconsistent with the input. And the probe shows that the encoder plays a role in determining whether content is omitting in the output, sorry. Okay. So the second part of the talk, I wanted to talk about conditional generation for dialogue. And so again, how can we better understand, better explain the behavior of a dialogue model, and specifically how this behavior impacts the coherence and the cohesion of the dialogue, of the generated dialogue. And here we are in a context where we generate, so the idea, the task is to generate given a dialogue context, which is, so the dialogue is always a set of, a sequence of question-answer pairs. And each question-answer pair is grounded in a knowledge-based triple, in a fact. Right? So you can think of it as a tutoring dialogue. You're asking basically, the dialogue is a sequence of question-answer pair about entities that are related within a knowledge graph. So the input to the task is a dialogue context. It's also a knowledge graph, which is a subgraph of Wikidata, for example. And the task is to generate the next question. And so what we wanted to look at is to have a way to assess, why, to have a finer grain assessment of, how coherent and how of the dialogue coherence, factuality, and coherence. So for coherence, we want to know, did the model select a turn or generate a turn that is relevant with respect to the dialogue context? is there any repetition? So is a generated turn repetitive with a previous context, with a previous dialogue? Is it factually correct? I mean, does a question match a fact in the knowledge base? And we also looked a little bit at cohesion. So, you know, in dialogue, you have a lot of pronouns. So are those pronouns used properly? And so what we did here is, normally when you, well, often dialogue models will just generate a response from the context. But what we did here is, instead of directly generated, you know, the next question from the context, what we did is we generated two things. First, a triple, and then a question. And the idea is that this intermediate, this added, I mean, the triples you don't actually need for the dialogue, right? So the idea here was to produce this intermediate results, the triple, to have a better, to have a more transparent understanding of what was going on in the model. I'll just explain a little bit more. So basically, the idea is this: you have as input, again, it's an encoder-decoder. So as input, you have the knowledge graph, from which you should retrieve the information that supports your turn. And there is a dialogue context what has been generated previously. You encode both of these, and then you decode from the representation produced by the encoder. But instead of decoding just the next question, you first generate a text, a fact, and then you generate the question. And what this allows us to do is to have, again, a sort of more transparent analysis of what's going on. It allows us to look at factuality, so because we can look at the predicted fact and check whether it's in the knowledge base. Then we can look at whether the question actually matches the predicted fact, and if both are true, then we can assume that the question is factual. So it gives us a sort of easy way to check whether the question is actually factual without having to compare a natural language question with knowledge-based triples. It also allows us to better understand how much the prediction impact dialogue coherence by checking whether the predicted fact is actually different from the fact that has already been predicted. Is it new, or is it a repetition? And is it relevant? So does it belong to a set of facts that is actually relevant for the current dialogue context? And finally, we can also look at dialogue cohesion, because so the question is actually associated with a triple. So the pronouns can be associated with entities. We can check the genre of this entity and whether it matches the genre of the pronoun. And we can also check for ambiguity. I'll come back to this later. So this was it. Sorry. Okay, so again, so we use this data set here, the Kajikonf dialogue data set, which consists of about 70,000 dialogues. And again, so the dialogues are a sequence of question-answer pairs, where each question-answer pair is associated with a knowledge-based fact. And as input, we have this subgraph of the knowledge base. And one thing we wanted to see is how well does the model learn to retrieve or to predict facts that are relevant to the context. So to do this, we added to the knowledge graph that was associated with the dialogue distractors, right? So basically, the knowledge graph associated with a dialogue in the training data is actually a set of facts that are relevant to that dialogue. But what we did was to add some distractors, so facts that are not relevant to the dialogue, to see whether the model would actually correctly not predict those triples, those facts. So we added 3 types of distractors, some of them which are more or less similar to the relevant triples. So the first type of distractors are facts where the subject is of the same Wikidata category as a dialogue root entity, so the entity the dialogue is talking about. So the triples talk about entities that are similar to the entities the dialogue is about. The other one is the same thing with properties, so we take a property that is associated with the dialogue, but the triple is not relevant to that dialogue. And the third one is just a random triple that have nothing to do with the current dialogue. And then we also experiment with different types of contexts because we have, we can either take train on the context where you have only natural language or only triples or both. And also we had one option where you take only the question, you ignore the answers. So here we have, the first thing we do is you can, because you predict a triple in addition to the question, you can directly check whether, how much of the triples are actually relevant. So you can analyze relevance. And so the part highlighted in blue indicates how many of the triples that are predicted are actually those distractors, right? And so we see there's very few of these distractors are selected, so between 0 and 2%, depending on the type of dialogue context we train on. So we do have some fake facts. So we do generate sometimes facts that that are actually not in the knowledge base. So that's about 2%. So here we can see that the model is going to generate things, hallucination basically. And then answer matter, yeah. So here again, it's still about relevance. So we see there's few incorrect triples for most models, so at most 3%. But the answer matters. So we have this, as I say, we have this context where we do not take into account the answer. So we actually remove some information from the dialogue context. And then we generate a lot more incorrect triples. So it's important to keep all the information in the dialogue context. So we have, to summarize, so we have high relevance. Most of the triples that are predicted are relevant and correct. And then what we do is we compare the generated question with the triple using bleu, so basically the overlap in terms of n-grams between the question and the triple, and we see it's very high. So we can, so this gives us an indication so the question that is generated is actually verbalizing the content, verbalizing the triple, the facts that has been predicted. So the idea is if the fact that is predicted is relevant to the dialogue context, and if the question matches this triple, then the question, the natural language question, is actually relevant to the dialogue context. And the final thing we did was look at pronouns. And as I said, so again, because we have, the question is associated with a triple, and the question is always about the object. So if there is a pronoun in the question, it has to refer to the subject of the triple. So we can check, and the subject of the triple is an entity in Wikidata, so we know it's Jean from the knowledge base. So we can check whether the genre of the pronoun is actually correct. Right? So where was he buried? Then we can compare he with William Herschel. From the knowledge base, we know William Herschel is a man, and so he is correct. And the other thing we can do is we have a heuristic to measure, it's really a very rough heuristic, to measure, how many of what is the ratio of pronouns that is ambiguous in the sense that the last entity of the genre, of the same genre as a pronoun mentioned in the dialogue context, is not the referent of that pronoun. Right. So here you have what was the name of Herschel's teacher, then Neville something something. So he's a man. And then the next question is where was he buried? He is intended to refer to William Herschel, but the previous noun phrase that was of the same genre, so that was a male, is not actually the expected antecedent. So this is what we would call a case of ambiguous or not ambiguous pronoun. I guess it's not. The context does not lead to the most to the intended referent. So here you have some numbers, but basically the idea is what it shows is that you have a good. One thing we see is that there's a good proportion of questions that contain pronouns, so between 8 and 13%, which is important because in dialogue, if you want to have a dialogue, a natural dialogue, you want to have. You want the model to actually introduce pronouns. We see that there are differences between contexts. So in particular, if the context is only the triple, the facts, then you have a higher rate of pronouns, for which we don't have any good explanation. And there is a strong bias for masculine pronouns, probably due to the Wikipedia data, to the fact that it talks more about men than women. We also observe that there's a good diversity of triples giving rise to pronominal questions. So it's not the case that specific triples systematically triggers pronoun, but it's much more diverse. And the antecedent pronoun-genre agreement is quite high, so 95 to 96%. And the proportion of ambiguous pronoun is also quite high. But again, I mean, it's really a heuristic we're using here, so this will need looking into more detail. Well, then we did some, maybe I should stop here, right? If people want to eat. Well, we did some ablation on the knowledge graph and on the data context, which basically show that both of them are necessary for generating relevant terms. So in conclusion, I think, so what we did here is fairly specific to the specific task and the specific setup. And I think, now that we have these super powerful language models that generate very good text, can do a lot of things, it's really important to be able to come up with ways of understanding what kind of errors these models are doing, being able to quantify them and trying to understand where these errors come from. So I will stop here. Thank you.
Are there any questions? Okay. Well, let me start then. So I think there's sort of an elephant in the room. You kind of touched on it in the end, which is, I think this line of research sort of predates all the excitement about ChatGPT. And I'm kind of worried that there's a success catastrophe with ChatGPT. The success is that everyone's heard of it, just everyone's heard of it, okay? The catastrophe, I think, is that at some point, they're going to get tired of the fluency and they're going to start to be concerned about some of the things you mentioned. I think hallucinations are probably more of a problem than omissions. But I'm wondering, is there a way to connect the dots between this line of research and that elephant?
And that what?
Elephant, the ChatGPT.
Yeah, so as you said, hallucination is easier to detect somehow. You can do, you can try to match whatever the model is outputting with known facts or with a knowledge base. So I guess it depends also on the specific generation task you are considering here. So I'm not sure that, for the task I was presenting, for example, converting graph to text, that those omissions are disappearing. So you still have those issues coming up here.
So I'm still hoping there'll be a question, but since there won't be, I'll just keep going. So I'm noticing that the younger members of my team are starting to use ChatGPT in creative ways. And one creative way is to, it's sort of instead of Stack Overflow or a man page, if they want to know how a subroutine works, they just ask ChatGPT. Now, I would have thought, given this kind of work and my experience with hallucinations, this would be an accident waiting to happen. But I think that the field is figuring out when to believe it and when not to. Is there a way to sort of evaluate how well ChatGPT could do compared to Stack Overflow, and could something like what you're describing be useful for that?
I mean, for the code, one thing is this code is executable, right? So you can look at the results. That's a bit different, right? So, for example, also for semantic parsing, so executable semantic parsing, where you want to convert a natural language query to a knowledge base query. You can give this to ChatGPT and see, does it actually give you the expected results, because it's executable. So that I guess that makes it a little bit easier to verify. I think for the text, when you generate hallucination, it's a much harder problem to find out. We discussed it yesterday, but how do you find out that the text that is generated is actually factually incorrect?
Well, all right. Sanjeev, did you have a question?
I'm still formulating my question, but so I was thinking about generation in a slightly different setting, where, or maybe it's kind of covered by your dialogue evaluations, but not the way you evaluated it. I'm thinking of it more as a information-seeking dialogue, where there is another part which requires identifying what the question is and relating it to some section of the knowledge graph, saying this bit of the graph contains the answer to the question that was asked. Mm-hmm. And then evaluating this question of semantic adequacy, as well as I guess you can think about both. You can think about whether it gave the answer, all the information in the graph that is relevant to the question, where omissions would be important, mm-hmm. and also whether it generated something that is irrelevant. It's not hallucination, but there are things in the graph that are not relevant to the question, but it generates things. So I was wondering whether there is any work in that space, because this then goes back to how to tie ChatGPT with task-oriented dialogues, where there is a backend of some sort, maybe a knowledge graph or something, and ChatGPT is trying to answer your questions based on that, rather than making them up out of thin air. Is there work in that space where you evaluate both the adequacy and maybe the extraneousness in the response relevant to a question?
Mm-hmm. Not that I know of. I mean, there is this more like executable semantic parsing, where you check. So you have this natural language. I mean, it's a dialogue, and you convert systematically the dialogue turn to a SPARQL query that is checked against the knowledge base. But mostly people want to get the right answers. I don't think there is any work that. I mean, usually the answer is also a simple fact. So it's not like it's going to give you multiple facts. Some of them are not relevant.
I was thinking more. The answer might contain joining 2 or 3 triples in the knowledge graph and saying, oh, this is Obama's elder daughter, and this is her name, and this is the college she goes to, and therefore this is the answer to the question. So you take 2 or 3 triples and you generate.
So that would be the multi-hop question answering. Yeah. So this, in a way, so this is. You have these approaches where you try to answer a question for which the answer has to be deduced from several triples, right, which are related somehow. And one thing that is that makes it a bit more explainable is the multi-hop reasoning, where you decompose a question into sub-questions, and then you can explain the final answer by showing what is the answer to each of the intermediate questions. So that would be one way. Yeah.